All right, guys. Are there any questions on any of the assignments thus far? Any questions on any of the assignments? All right, guys, let's put the computers away. So, what we started with on Friday was solving these higher degree polynomial functions. And for the most part, we graphed them to see if we could find the solutions and then worked and used the quadratic formula from there. The next thing we're going to look at is the rational root theorem. And the rational root theorem states if f of x is equal to this here, which is really just describing any possible polynomial function of higher degree, and has integer coefficient, then every rational solution of the function f of x equals 0 has the following form. And that's really what's important, is the p over q, where p is the factors of the coefficient and q is the factors of the leading coefficient. Rational root. And what this will give us is all of the possible rational zeros, p over q. And that'll help us to be able to solve any of the higher degree polynomial functions. So we need these rational zeros. Noted from last Friday. So looking at this here, we want to find all the real solutions of this function here, and we're going to find the rational zeros first. So to find the rational zeros, we need p and q. P is going to be all the possible factors of the constant term, and q is all the factors of the leading coefficient. Now, when we look at this here, our constant term for this equation here is 20. So we look at all the factors of 20. Well, we'll have 1 and 20. What else did we have? 2 and 10. And these here would be all the possible factors of 20. So that would be all of our factors of the constant term. Any questions on this here so far? Now we need to find the factors of the leading coefficient, which would be well, 1, because the leading coefficient is 1. Now our list for this here is going to be p over q. So we're going to divide each p term by each q term. Now for us, we only have, for this one here, there's only one q value. It is 1. And we're going to put plus or minus in front of it. So we're going to do 1 divided by 1, which is 1. Then we can do the next one, which would be 2 divided by 1, which is 2. Plus or minus 4 divided by 1 is 5 divided by 1 is 5. 10 divided by 1 is, and then plus or minus 20. And we'll always have the positive or negative case. We're going to take both. Now at this point here, if we had another factor for q, we would move on to it and do the exact same thing, dividing each one. So if there was another number, we would do p over that number. But what this has given us is all the possible rational zeros all the possible rational solutions for this function. Any questions on this so far? So if there is a rational solution, a whole number or fractional answer for this polynomial equation, it will be in this list. Now when we look at this here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible rational solutions. But how many solutions can we actually have? 3, because it's a degree 3, there's only 3 solutions. So only 3 of these numbers will actually work, if at all. Because we could have non-rational solutions, or we can have solutions that are not going to be rational, because they could be complex, they have I in them, or they could have radicals. Now we're going to figure out which ones work with synthetic division. So across the top we'll have our coefficient, so 1 will be with x cubed, negative 8 is with x squared, 11 is with x, and then 20. And our first part of synthetic division will be to bring down the 1. Well, we'll start with 1 and do synthetic division with it. Well, 1 times 1 is 1. Negative 8 plus 1 is 1 times negative 7 is negative 7. 11 plus negative 7 is 4. 1 times 4 is 4, and 20 plus 4 is 24, and that is our remainder. So is 1 a solution? No, because we needed it to be what? A remainder 0. Okay. So 1 doesn't work. Then we can do negative 1 next. Because we're just going to keep going through the list to see which ones work. So we can do negative 1 next. And try it again. Negative 1 times 1 is negative 1. Negative 8 plus negative 1 is negative 9. Negative 1 times negative 9 is 9. 11 plus 9 is. And negative 1 times 20 is negative 20. And 20 plus negative 20 is 0. So we found the first solution, because we got a remainder of 0. Okay. Well, at this point here, we can move on to positive 2 and see if we get a 0. If not, then we move on to negative 2, then 3, negative 3, 4, negative 4, 5, negative 5, 10, negative 10, 20, and negative 20, and see if any of these work. And it could be that 2 of them work, or it could be that none of the rest work, and negative 1 is the only real or rational solution. But what is the degree of this function here? Because it started out as a degree what? 3, yes? And each time that we find a solution, it takes the degree down 1, yes? So it was a cubic degree 3, now it's at what, a degree 2, yes? Now we could go through and try to find another one, or we could plug the variables back in and use the quadratic formula. Because really, once we get this down to a degree 2, a quadratic, we can throw it into the quadratic formula, and it'll give us the other 2 answers. Give some extra space. So really what we have now, and what we have left, is x squared minus 9x plus 20 is equal to 0. Or negative b, plus or minus the square root of b squared minus 4ac all over 2a. The number in front of x squared is our a, the number in front of x is b, and the constant term is our c. Yes? Mm-hmm. Let's wait. So, looking at this here, we need to plug in A, B, and C. Well, what is the value of B? Negative 9. So our negative B, negative 9, is just going to be a positive 9. Inside the radical, we're going to have negative 9 squared minus 4 times, well, A is 1 and C is 20. All over 2 times A, or 2 times 1. Plus or minus 2 square root. Now at this point here, we would want to plug everything that's inside the radical in first, just in case, because we wouldn't want to use the radical, just in case the graphing calculator, if we're using it, it came out to not reduce completely. And we want to hold on for the yellow calculator, just in case it's a negative. Now if we type this in, negative 9 squared is going to be positive 81. Because 9 times 9 is 81. 4 times 1 times 20 is going to be negative 80, which would give us 1. And the square root of 1 is, you all know, 1. Because the only number times itself that gives us 1 is 1. If we take any root of 1, it'll still work out to be 1. Well, can we do 9 plus 1 and divide it by 2? And we can also do 9 minus 1 and divide it by 2. Well, 9 plus 1 is 10, and 10 divided by 2 is 5. 9 minus 1 is, and 8 divided by 2 is 4. So 5, 4, and negative 1 would be the solutions for this here. Now, are 5 and 4 part of our rational zeros that we got in that list? Well, yeah, all the rational zeros would be there. Well, also, since these are whole numbers, could we have gone on and just graphed it? Well, yeah, if it's whole number solutions, we could have graphed it and it would have given us the answers. But whenever we're dealing with these here, especially if the graphing didn't give it to us, we need to get it down to a quadratic. Because if I can get it down to a degree 2, then we can use the quadratic formula, and it would factor and give us the rest of the solutions. Not factor, but it would tell us what the remaining 2 solutions are. Any questions on this here? All right. We're going to skip over to this one here because the other 2 aren't as interesting because the leading coefficient is 1. It's not as interesting as this one here because the leading coefficient is 10. So this one's a little bit more interesting than the others. So to get started, we're going to find all of the possible rational zeros for this here, our P and Q. Now our constant term in this case is 12, so we want to find all the factors of 12. Well, that would be 1 and 12, and then 2 and 6. Are all the factors of 12. Now we need to look at the factors of 10. Well, the factors of 10 are going to be 1 and 10, 2 and 5. Let's do that in black. Now we want to find P over Q. I always start out with q being 1, and then we'll progress from there. And we want to divide each of the values of p by our first q, which is 1. So we'll do 1 divided by 1, which is 1. Then we'll move on to 2. 2 divided by 1 is 2. 3 divided by 1 is 3. 4 divided by 1 is 4. 6 divided by 1 is 6. And 12 divided by 1 is 12. So really with our first value of q1, we're just really rewriting all the values of p over. Any questions on this so far? Now we're going to move on to where q is 2. Now if there's any values that repeat, we don't write them again. We only have to have them once. We don't need them 2, 3, or more times. So we'll start out with 2 divided by 1, which will be plus or minus 1/2. Then what would we do next? 2 divided by 2. Well, what is 2 divided by 2? 1. Do we have it listed? Yeah, we don't need to write it again. Then we can move on to the next one, 3 divided by 2. Well, 3/2 doesn't reduce, so we have 3/2. Our next number after this would be what? 4. 4 divided by 2 is 2. Do we have that? Yeah, so we don't need to list it again. Then we can move on to 6. 6 divided by 2 is? We have it. And then lastly, 12 divided by 2 is? We have it. Well, now the next one we can look at is 5. So we'll start out with 1. 1 divided by 5 is going to give us 1/5. Then we can move on to 2 divided by 5. Well, that would be 2/5. Then we can do 3 divided by 5, which is plus or minus 3/5. Then we would do 4 next. 4 divided by 5 would be plus or minus 4/5. Then we'll have 6 divided by 5, which is plus or minus 6/5. And lastly, 12 divided by 5 is going to be plus or minus 12/5. And really we included all of them because none of our factors of p, 1, 2, 3, 4, 6, and 12, have a common factor with 5. So we end up having all of them. Now the last one we have is 10. So we can start out with 1. So we do 1 divided by 10 is going to be plus or minus 1/10. Now we can look at 2. Well, 2 divided by 10 is 1/5. Do we have it? Yes. Then we can look at 3. Well, that'd be plus or minus 3/10, because that won't reduce. Then we would look at 4/10. Well, 4/10 will reduce to 2/5. So we already have 4/10. 6/10 will reduce to 3/5. And 12/10 will reduce to 6/5. So these here are all the possible rational zeros for this here. So if we look at this here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and there's 2 of each. So we have a total possible of 32 rational zeros. But only how many answers? 4, because the degree is 4. So only 4 of these will work. Well, what can we do next? Well, we could, what? We could graph it. So we can type this into the graphing calculator to see what zeros we could get. So we'll type it in as 10x to the 4th minus 11x to the third minus 42x squared plus 7x plus 12. So we'll type this whole thing in. And once we get the whole thing in, typed in, we're going to hit what? Graph. And we're looking for the spots where it crosses the x-axis. And how many times does it cross the x-axis? 4. We have 4 distinct times that it crosses. And we needed how many solutions? 4. So each one of these would be a solution. And how many times would each one occur? Once, because it crossed. It would also be an odd number of times. So we could have 1, 3, 5, 7. But because we do have all 4 locations, it's just going to be 1. Now we can do second table. And do we have any zeros at whole numbers? Well, no, right? They do cross, but none of them are whole number solutions. So if we look at the graph between, going from left to right, we do have a 0 between -2 and 1. Yes? But it's kind of closer to -2. We also have a 0 between -1 and 0, yes? Is it closer to -1 or closer to 0? It looks about in the dead center, doesn't it? Between -1 and 0. So it's pretty close to the middle. Then we also have a 0 between 0 and 1. And I would say it's kind of closer to 1. And then we have a 0 between 2 and 3. And it's definitely a little bit closer to 3. And it definitely didn't give us any whole numbers, did it? So when we look back at this here, our possible rational zeros, out of all these here, well, we can say for certain it's none of these, because it can't be a whole number. If it was, it would have shown up on the calculator. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So we got rid of 12 of those possible rational zeros. So what we're left with are these here. And what we can use are the places where it crossed to figure out which rational zeros are most likely to work. Well, the one that's between 2 and -3 is pretty far out there, because we're looking for a number close to 3. Now, looking at all the remaining fractions, which one of them would be close to 3? 12/5. Because 12/5 is the only one that's greater than 2, yes? Because 1/2 is less than 1. 3/2, that's less than 2. 1/5, 2/5, 3/5, 4/5 are all less than 1. 6/5 is less than 2. 1/10 and 3/10 are both less than 1. Because 12/5 is 2 and 2/5. It's the only number greater than 2. So if we're going to have a rational zero for that spot, 12/5 would be the one that it would occur. Now across the top, we will use our coefficients. So 10, -11, -42, 7, and 12. And then we would bring down the 10. Corey, Colin, Ace's brother, Pendleton. Let's focus up. Guys, let's heads up. Thank you. So we set this up here, we're going to try 12/5. So the first thing we're going to do is 12/5 times 10. And these would cancel, give us 2, and 12 times 2 is 24. And really, we could be plugging these into the calculator. Because if you've been doing these in the calculator is not that bad. Because we could start off with, turning it on, 12/5 times 10. And then we would add to it -11, which would give us 13. And then we'd multiply 13 by 12/5, which would be 156 over 5. And then we would subtract from it 42. Which works out to be -54 over 5. And then we would multiply it by 12/5, which is going to be -648 over 25. Well, hold on. Is this getting anywhere close to 0? No. So we can stop here. And erase all this here. Erase this here. So 12/5 doesn't work. Well, is there any other possible number between between 2 and 3 that we could have for these rational zeros? Well, were any of the other numbers bigger than 2? Well, no. So most likely, between 2 and 3 is not going to be a rational number. It's going to be irrational. Because the zeros that we listed here are only the possible rational numbers. They're not going to be all of them. So most likely that answer has a square root of some kind that doesn't reduce. Or it could, and that's going to be it. Now, it's not going to be imaginary. We're not going to have I terms. Does it actually cross the graph? Well, yeah. So it's going to have a number. It's just not rational. So let's look at the other ones. Wait a minute. Where was the one between -1 and 0? It looked right in the dead center. So it could be what? Well, if I have a pen. Well, it looks like it could be -1/2 because it sits right there in about the middle. And we can try it. Well, -1/2 times 10 is going to be negative, and 1/2 times 10, or 10 divided by 2, is 5. -11 plus -5 is -16. Okay, that looks good so far. -1/2 times -16, the negative and negative would make a positive. 16 divided by 2 is 8. Okay. -42 plus 8 is going to be -34. Okay, that's working out well so far. -1/2 times -34, the negative and negative would make a positive. 34 divided by 2 is 17. 17 plus 7 is 24. Now, -1/2 times +24 would give us a negative, and it would be -12, because 24 divided by 2 would be 12. 12 plus -12 is 0. X is equal to -1/2. So we found that 0. Now that's taken it from a degree 4 down to a degree 3. If I can find at least one more, then we can use the quadratic formula and it would give us the other 2. I wouldn't try -3/2. I would look at 0 and -1, 0 to -1, or 0 to 1. Because with these irrational numbers with the square roots, they always come in pairs. They're always going to come in pairs. Well, this one was already at the biggest, yes? So where do we think its pair is going to be? Most likely the other pair is going to be on the other side. They're going to go together. So if they're close to 0, close to the y-axis, most likely the other one's going to be close. Since it's farther away, most likely the other one's going to be far away. It may work out that way, it may not. But let's try 0 to 1 first, and it's closer to 1. So we can try 4/5. Bring down the 10. So we can start off with 10 times 4/5. And if we plug that in, we would get 8. Negative 16 plus 8 is negative 8. And then we would do 4/5 times negative 8, which would be negative. Is this going to probably get 0? No. I mean, if we had fractions or ways that the numbers would eventually work out, then yes. But this here is not going to get us closer to 0. So 4/5 doesn't work. Let's move one over and try 3/5. So we can do 3/5 times 10, which is almost 6. It would be 6. Now set negative 16 plus 6 is negative 10. Well, negative 10 times 3/5 would be negative 6. The only difference was that the 10 was negative instead of positive. Then we can add straight down. Negative 34 plus negative 6 is negative 40. Then we do 3/5 times negative 40, and we get negative 24. Which does give us a 0. And this here is really why the rational zeros is helpful. Because graphing normally would not have given us negative 1/2 or 3/5. But combining it with the rational zeros, we could get somewhat close to where the zeros should be occurring. And we could find it with the rational zeros. And what that leaves us with is if we plug the variables back in, 0 would be our remainder. Negative 40 would be the constant. Negative 10 would be with x, and 10 would be with x squared. So what we have is 10x squared minus 10x minus 40 is equal to 0. Since we got it down to a quadratic, we can use the quadratic formula to find the remaining 2. Now, one piece of helpful information, is there a greatest common factor between these 3 terms? 10, yes? We can leave it in there, or we can divide each one of them by 10. We can get rid of it. Because if we leave it in there, when we get to the very end with the quadratic formula, we'll have to pull it out anyways. We'll have to reduce it out. So why not reduce it now, then once we get it to the end of the formula? And if we divide it out, what we get is x squared minus x minus 4 is equal to 0. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Now looking at this here, the value of b would be what? Negative 1. So our negative b, negative 1 would be positive 1. Plus or minus this negative 1 squared minus 4. Well, A is 1 and C is all over 2 times A. Well, A is still 1. 2 times 1 is 2. Any questions? We have 1 plus or minus. So again, we want to plug what's inside the radical into the calculator first. We don't want to use the radical just in case it doesn't simplify out, and most likely it won't. Well, negative 1 squared is going to be 1 minus, well, 4 times 1 times negative 1 is negative 16, which adds together, you get 17. Do we get that? Yeah. That's right, you just add them together. Can we take the square root of negative 17 and get a whole number? No, because the closest one to it is 16, because the square root of 16 would be 4. Square root of 17 does not have a whole number. And that's as simplified as it gets. So those are the other two answers. Because we'd have 1 plus the square root of 17 divided by 2, and 1 minus the square root of 17 divided by 2. Because those would be our other two answers with x is equal to negative 1/2 and 3/5. Any other questions on this here? We good with this here? Now there is one interesting thing I want to show you, and that's dealing mainly with the division of 10, because we had 10x squared minus 10x minus 40, because this was our one equation that we had, yes? Now we divided everything by 10, which left us with x squared minus x minus 4. Now these look like very different equations, but just the numbers in front changed, yes? But what's interesting is if we look at the two graphs, the overall graphs are different except where they cross the x-axis. They cross at the exact same point. That's why we can do this. It's just changing that scale factor of everything else. But we're only caring about where it crosses the x-axis. So that's why we can do this division of 10. It doesn't change where it crosses. So it crosses at the same spot, but everything else is different. Any other questions on this here?